Hello, everyone, and welcome to this exciting world of CAM programming and CNC. The acronym CAM stands for Computer Aided Manufacturing. We will be using Fusion 360's built-in CAM function to create a toolpath that will be converted into G-code via the post-processor in order to remove material on a CNC. We're making a part from scratch. This process starts with you, the engineer. You will be using your engineering knowledge and expertise to design a quality part prior to machining. Quality engineering will help to lower prototype cost and help to minimize failure. Prototypes and recalls are expensive. That's why engineers make the big bucks. This is a flow chart for making a single part from start to finish. The majority of the time is spent in CAD program, giving the user the ability to fit assemblies, determine restraints, and run analysis. A CAM program is then used to create toolpaths prior to post-processing, which converts the software program into G-code for the particular machine. The simulation will help prevent errors prior to machining setup. Optimization is used to speed up the machining process in order to minimize cost. This is an ongoing process that happens in each step of the flow chart and usually starts over, during and after machining the first part. Finally, machining, the process of removing material, in this case, controlled electronically on a machine. You tell it what to do, and it does your bidding. First thing you want to do is to create your Fusion 360 account and sign on. If the program asks for a team name, just make something up. It is not necessary for the scope of this class. The next step is to create a file folder on your computer so that you can easily access it, because we're going to be downloading files from the website and you will need to remember where they are. Now let's head over to the website. You can access it by simply searching for MAE Machine Center and clicking on the first tab. Our website is full of useful information and it would benefit you to spend a little time navigating it. For this class, we will head to the menu on the left and click on CNC Machines. Here you will see the two mills in our lab and corresponding post-processors highlighted in blue. Click on the Tormach 440 post-processor and download it. Scroll down the page a bit and find the mill tool library and download it. Finally, download the sample part 1 located below the tool library. Once you've downloaded these files, transfer them into a file folder you've previously created. We will no longer need the website for this section, so you can close it out and return to the Fusion 360's home screen. On the home screen, you will want to verify that your name is on the top right corner of the screen. If you are more familiar with the controls for SOLIDWORKS, you can easily change your preferences by left-clicking on your name and then selecting Preferences from the pull-down menu. Another menu will appear where it says Pan, Zoom, Orbit shortcuts. You can change between Fusion defaults and SOLIDWORKS. You can now close this program out. Scroll to the top left of the screen and locate the data panel and open it by clicking on it. Fusion is a cloud-based program. Therefore, by default, all of your file folders are saved on the cloud instead of locally like in SOLIDWORKS. You can also share projects between groups, edit, and update projects all on the cloud. You want to create a new project, label it, and use this project for everything in this class. Double-click on that file folder, and you'll want to upload the SOLIDWORKS file labeled Geneva Sprocket 440 that you pulled from the website, and select Upload. The loading screen will complete when it's done, and then you can close this menu. Double-click the item you want to open. Once open, you can hide the data panel to open up the workspace by clicking on either X or the data panel icon on the top left of your screen. Underneath the data panel, there is a workspace drop-down menu. We will use this to change our workspace from design, or CAD, to manufacturing, which is CAM. Now you will want to make sure that your model is in inches by scrolling over to the units and changing the active units to inches if it isn't already selected. Click on OK if a change was made. We will now set up our model in the proper orientation to designate a coordinate system. We want our model to match the way we will set our workspace up on the machine. You can use the mouse to move around the model, along with the Views block in the top right corner of the workspace. If you left click on the box, you can rotate the model. Clicking once on a particular view will orient your model to that view. We will be working with the bottom of the model, so rotate the model and click the bottom view. When you click on a view and one of the faces is normal to the screen, you will be able to use the arrows surrounding the view box to rotate the model. We want our model to have the x-axis of our model to be the longest measurement. On this model, it will be the splines of the gear feature running from left to right. Disregard the orientation of the view block. We're going to make our own coordinate system. Before manufacturing, it is important to have an understanding of how the part will be made. There are limitations to design concepts that are based on cost, expertise, and shop capabilities. These need to be taken into consideration during the design phase. For instance, we designed this part originally to have a round feature at the bottom of the model. It may have been possible to create a jig in order to hold this round feature in place for the second operation. But because that feature was non-critical, it would be cost-effective to flatten the sides to allow this feature to be easily fixed in a vise. If you do not know which side is your long side of your model, you can use the inspection tool to obtain the length and height. This also comes in handy while selecting your material. The material selected must be larger than your model on every axis. In the machining world, fixturing is one of the most important skills to learn. How you fix your material can speed up or slow down the entire process. You can have fixtures that can make multiple parts at once to speed up the manufacturing process. Here is a picture of a fixture that holds 16 parts at once. With production like this, the fixture is generally included in the model to avoid tool collision. We will be using the most common fixture in a machine shop, the machinist vise. It is important to know which length of the material needs to be clamped. If possible, you want to hold your workpiece with the greatest surface area along the vise jaws and the shortest distance between those two jaws. Now that we know how we plan to fix our workpiece, it is time to start a new job. Click on the Setup menu and hit New Setup. The setup box will appear, and for the operation type, we will be using the milling operation, which is selected by default. For your orientation, click on the drop menu and select XY axis. Your X-axis is selected by default. If not, select the X-axis now. You want to click on an edge that is parallel with the X-axis that you want to use for your coordinate system. Remember that the X-axis is going to be the longest length and follow the splines of the Geneva drive. In fact, I can use those splines to select my axis. If I accidentally selected the face, I can undo this selection. Click on the X-axis selection again and click X to clear the selection. Then select the appropriate edge. You can also rotate your model to get a better view of the edge you choose to select. Now select an edge following the Y-axis. As you can see, the Y arrow is facing in the opposite direction of our machining orientation as shown in this diagram. This picture shows the orientation of a standard machining coordinate system. You can see that X positive is facing to the right, Y positive is facing away from the operator, and Z positive is facing upwards. Now you can change the direction of your axis by clicking Flip Y-axis. As you can see, now our coordinate system is correct. The X-axis is facing to the right and the Y is facing up or away to the user. Machining standards use the top left corner as the starting coordinate system. Make sure the origin is identified as the stock box point. Then click on the Box Point tab and on the top left corner of the model stock, rotate the model slightly to make sure that your orientation is correct. The coordinate system should be as follows. X is positive facing to the right, Y is positive facing up, and Z is projecting towards you. When you rotate the model to the view that it will be sitting into the vise, you can see that Z is positive facing up. Next, we want to set up our material stock in the next tab. Your mode selection will be Fixed Size Box. Now measure your block of material. If you do not have access to the material, You can copy my measurements and change them later if you are a student working in the lab. The material measurements must be larger than the model itself. If your material is undersized, you will need another piece. Be sure your screen looks like mine, with the coordinate system in the top left corner and the arrows are facing in the appropriate direction. Remember that your X direction is going to be your longest measurement. To read dial calipers, you want to take a look at the large numbers along the rail. More importantly, look at the hash marks. For instance, look at the number 1 and that its mark is on the right side of the number. It is easy to mismeasure when the slider is close to a number but does not surpass it. Just keep in mind when using calipers, the mark between the numbers indicates 100 thousandths or 0.1. Then you look at the dial. Each number is 10 thousandths or 0.01, and the marks in between those, in this case, are 5 thousandths or 0.005. Most calipers will have 10 marks in between the numbers indicating 1 thousandths or 0.001. A few things to point out in this picture. The blades are where you measure on dial calipers. They have a cut along the reference edge on both sides. This allows to measure over small burrs and uneven surfaces, but this is not a measuring surface. The bezel nut keeps the dial from moving. The dial moves by twisting it clockwise or counterclockwise and can be used to zero the scale. When you zero the scale, you'll want to make sure that the blades are clean of any debris. The lock screw locks the scale in place. Finally, the depth rod measures depth. The internal, external, and depth measurements will be the same at any given distance. Dial calipers are normally accurate to within their scales. However, because of their nature and operator use, I wouldn't use them for tolerances 5 thousandths or less. You should now measure your material and fill in the X, Y, and Z. Remember that your longest edge, the edge that will sit along the vice jaws, is going to be your X coordinate. If one of your measurements is undersized to your model, you can see that the model sticks out amongst your stock and it'll turn red inside your view window. The measurements I got were 2.51 for X, 2.31 for Y, and 0.48 for Z. All of my model positions will be centered. That means the model will be floating in the center of your stock with excess material on all sides, top, and bottom. Once you have your measurements, click OK. Never hit enter on your keyboard for this program or it will remove your progress and make you start over and feel like a... Okay, what we need to do now is to insert our tool library. The tool library will be specific to the tools that you have. The individual tools can be modified in the library to adjust to the machine's capabilities. We have taken the liberty of pre-programming the tools so that it fits the capabilities of the Tormach 440 mill that you will be using. Click on the Manage drop-down tab and select Tool Library. Right-click on Local and select Import Libraries. You'll find the tool library where you have saved it from the website. The first operation we need to tackle is 2D facing. Click on 2D and select Face. Click on Tool Select and pick tool number 1. That is the 3/4 inch face mill. The rest of the information shows you the running conditions for the tool, such as feed rate and spindle speed. These conditions have been pre-programmed for you. Just remember that these values will change with the material selection and the machine's capabilities. They can be changed in the tool library or on the fly in this particular window. Take a look at your geometry tab and notice that your model now has an outline around it. This is your perimeter of your facing operation and is normally fine by default. For your heights, your clearance height will be from retract height with a 0.2 inch offset. Your retract height will be from feed height, again with a 0.2 offset. Your feed height will be with a 0.2 offset from your top height. Your top height will be from stock top at 0 offset. And finally, my bottom height will be from model top with a 0 offset. I generally set these heights to be my default settings. To do this, right-click in each of the offset windows and select Make All Default. The next time you do this operation, it will be set up this way, even on a new project. Do not set your top height or bottom height to default as these constantly change. Don't worry about what these heights mean right now. I will cover them in the second lecture. We don't need to change anything in the other 2 tabs, so just click OK. Now you'll be able to see the tool path that the program created. Our next operation will be 2D adaptive clearing. We will use the same tool as before, so by default it should be selected. That is the 3/4 inch face mill. Tool number 1. Feeds and speeds are set up, so click on the next tab and select this contour here. As you can see, I can click on the face, but that will drastically increase my tool path. For the heights, we will use the same heights as the previous operation. That is clearance height from retract height at 0.2, retract height from stock top at 0.2. The top height will be model top. It won't be stock top this time because we removed that stock on our previous operation. The bottom height will be selection. This allows you to select a face or feature. We will select the top face of the gear. Once again, make your heights default with the exception of your top height and bottom height, which constantly change. Under the passes tab, check the box for stock to leave. And we will leave 20 thousandths or 0.02 of radial stock and no axial stock. The reason we'll be leaving stock on the sides of this part is because adaptive clearing is a roughing operation, and so we will come back to this with a finishing operation. You will get a better finish if you remove a small amount of material. We only want to leave material on the sides, which is radially. If we left stock axially, that means that the entire face would be 20 thousandths higher during the finishing operation. With a 1/4 inch end mill, it would leave a valley along the entire contour. You should make the axial stock default as we very rarely use stock to leave axially. We do not need to change anything in the linking tab, so just click OK. For the next operation, select drill from the drilling menu. We will start by drilling this hole. However, it is always recommended that you use a center drill prior to drilling to allow the drill bit to have a guide for its cutting edge. Here's a picture of a drill bit. If you take a look at the front face of the drill bit, you will see that this feature called the web is flat. That is parallel to the cutting plane. The bigger the drill bit, the bigger the web. This is why drill bits have a tendency to walk off center. The flutes that are machined into the drill bit allow for material removal through the length, but also makes them able to flex. The longer the drill bits, the more they will flex. The more flex they have, the more likely they are to wander. Here's a picture of a center drill. As you can see, all of the features are much shorter, and the tip of the center drill has a much smaller webbing, allowing a precise drill point that will minimize any wandering and allow for a guide hole for your bigger drill bits. Go to your tool selection and select tool number 2, the 3/16 inch center drill. Under the geometry tab, select the whole face. As you can see, an outline of the center drill is shown inside the whole feature. This is a good representation of the depth that the center drill will reach. Under your heights tab, your clearance height will be from your retract height and set at an offset of 200 thousandths. Your retract height set from your feed height at an offset of 200 thousandths also. Your feed height is from your top height with again an offset of 200 thousandths. You can set all these to default now if you so choose. Set your top height to whole top, as well as your bottom height. We will manually set the desired depth. Set the offset on the bottom height to negative 0.15 or minus 150 thousandths. Because we are moving in the negative Z direction, it will be minus. For the center drill, we do not need to change anything in the cycle tab, so click OK. Next, we will drill out this hole with a 3/8 drill bit. So under the drilling tab, select drill. Your tool selection will be tool number 7, the 3/8 drill. Under the geometry tab, once again, select the whole face. If I move the model to a parallel plane, you'll be able to see the depth of the drill. Get used to moving the model around. This will give you a good visual representation of your cam choices and will help to minimize mistakes. Let's set up our height. Similar to before, the clearance will be from retract set at 200 thou, the retract from feed height at 200 thou, and the feed height from the top height at 200 thousandths. Let's set the top height at the model top. Whole top works the same because the hole starts at the top of the model, but now you can see the heights. I changed to wireframe so you could better visualize the drill bit. As you can see, with the whole bottom selected, it only drills to the hole depth without piercing the bottom of the hole. We want to drill all the way through the center of the model. Therefore, we will set the bottom height to the model bottom. Next, select drill tip through bottom, and this will allow the hole size to be 3/8 throughout. No matter what material you use, the material will either flex, melt, or leave a burr on the underside. Because plastic is very soft and malleable, we'll want to make sure that we fully penetrate the bottom of the hole without leaving any burrs. So let's set the breakthrough depth at 100 thousandths. Two things to keep in mind. If I were to use the offset, I would need to use a negative value. The other thing to know is how much room you will have between the bottom of the model and your supporting structure. In this case, the vise. You do not want to drill or mill through anything unintentionally. On the mill, we will be using parallels high enough to clear all of these operations. Under the cycle tab, we need to change the cycle type to deep drilling full retract. This is important because you should only drill as deep as the diameter of the drill bit. This allows the chips to break free of the bit, minimizes tool wear, and allows the bit to cool slightly. With deep drilling full retract, the machine will peck at the hole instead of trying to muscle its way through. I like to set the peck depth at half the diameter of the bit when using a CNC. So let's set the pecking depth to half of 3/8, which is 0.1875, and click OK. We will be using this hole as the coordinate system on our second operation, so it needs to be precise. Not only are drill bits lacking in precision, but as you can see from the model, we're not at our desired diameter. For this next process, we will select 2D contour from the 2D menu and select tool number 4, the 1/4 inch end mill. For geometry, select the edge of the hole. For heights, clearance from retract height at 0.2, retract height from feed height at 0.2, and feed height from top height also at 0.2. Our top height will be from model top, and our bottom height will be from model bottom. Let's also set our bottom height to negative 20 thousandths or minus 0.02. You can now set these as default. It is important to remember when using an end mill not to cut deeper than the flute length. Let's talk about the flute. Oh, I don't know how that feral picture got in there. This is a picture of an end mill. You can see that the length of the cut is determined by the flute length. Try to cut deeper than this. The feature will taper because the shank is not a cutting surface and will leave a poor surface finish. The end mill we selected is indeed long enough to make it through the entire piece. So let's move to our passes tab and click on repeat finish pass. This should give us the type of precision and smooth finish that we desire. Oh, remember way back in the day when I told you that we would clean this contour up? Well, today's the day. Select 2D contour from the 2D pull-down menu. Your tool selection should already be tool number 4, the 1/4 inch end mill. Therefore, click on the geometry tab and select this contour. You could also have selected this contour because it's along the same path. You just have to make sure that your heights are correct. This brings us to the heights tab. If you set your heights as default on the last 2D contour, then they should already be set. If they're not set, look at the way I have them set up now. Change your top height to model top. Your bottom height should be from the option selection. And select the face of the gear. Make sure that you don't have any negative or positive offset on your bottom height because we want it to be parallel with this face. We don't need to change anything in the passes or linking tab, so click OK. Last step is to clean up any burrs. We will do this by selecting 2D chamfer from the 2D menu and selecting tool number 5, the 1/4 inch chamfer mill. For geometry, select the edge of the hole and the top edge of this contour. On your heights tab, your clearance height is from retract height at 0.2, your retract height from feed at 0.2, and your feed height from top at 0.2. You can also set these as default as well. Change both your top height and your bottom height to model top because we will change the depth of cut in the next tab. Under chamfer is where you can change your width and tip offset. Like most of these items in the program, you can hover the mouse into the box and it will let you know what you are changing. This is great reference material, not just for beginners, but also for seasoned programmers looking to refresh knowledge. Here we can see that this option controls how deep into your part you want a chamfer to go. 40 thousandths is a considerable chamfer, and since all we need to do is clean up the edge, let's use 15 thousandths or 0.015 as our width. Your tip offset needs to be at least as long as your chamfer width. If your tip offset and width are the same length, the bottom of the tooltip will be on the same plane as the contour you're cutting. This puts strain on the tooltip, and if your heights aren't set up perfect, you could leave an undercut in your finished product. The program knows the dimension of the tool because we program them into the tool library. The program will automatically calculate how to obtain the chamfer width given the tip offset.
Ain't that special?
Go ahead and click OK. Now you get to see how all of your hard work is going to pay off before you crash our so you don't crash our machines. What we want to do is right-click on Setup and select Simulate. Click where it says Tool, select Shaft, and this will make it easier to see without the tool holder in the way. Next, click the box that says Stock to show the starting material. The bar at the bottom is split up into your operations. You can see that it changes in the operation tree. I can also click and slide the timeline indicator to scroll through the operations. Any machine crashes will be shown in red. I can show you by changing the height of the 2D contour to have the tool holder collide with the workpiece. The tool will light up red and there will be red marks on the timeline. You can see if I press play, the simulation will start and I can speed it up or slow it down by using the bar here. Always simulate before setting up on the machine. This will save you many mistakes, but is not foolproof. You must always pay attention and make sure that all of your paths, and especially your heights, are right. After the simulation, you should be able to see the finished outcome of your first operation. When you're satisfied with your simulation, close it and we'll move on to the last stage of the CAM process before setting up the machine. The next step is post-processing. The CAM program is a widely used broad computing tool that covers most of the CNC applications, including 3D processes such as 3-axis and 5-axis mills, 2D processes such as lathes, routers, water jets, and plasma cutters. Each machine has its own parameters that the program needs to satisfy. The post-processor converts your CAM program into a language that the particular machine can understand as G-code. To find the post-processor for the Tormach 440, the one you grabbed from the website, you'll want to right-click on your setup and click on Post-Process, click on the ellipses, and find your file folder. For whatever crazy reason, the files don't appear in this folder, so you just have to have a little faith that they're in there. So click Select Folder. Under the Post Config, it should read Tormach Path Pilot Tormach 2. Under Properties, scroll down and where it says Optional Stop Between Tools, change this to No. Once you change it, it will remain blue to let you know that a change was made. This option is a redundancy and is not needed. The only thing to do now is to give your program a clever name so that you know it's yours. Then post the process wherever you can access it again. It will need to be on a flash drive to use on the CNC machines. However, it is just a file folder, so you can save it anywhere you want to access it later. And that's it. Congratulations. See you next time where we do the same thing, but on the other side.